and 3 p.m. for you. We can start. So we are very happy to have Dusko Pavlovic from the University of Hawaii to talk about concept mining and its relationship with categorical nuclei and tight completions.
Now I go. Okay. Okay, Zainab, thank you for exciting invitation, and everyone else, thank you for stopping by across the Pacific Ocean to listen to me. I have, as people in my age tend to have more to tell than I have time. So I think the general strategy should probably be that that we prefer clarity to coverage. So whenever I say something that any of you may not understand, please interrupt me and I will explain it. So wherever I get, let's try to make sure that everything I say is clear. Okay, so I'm going to begin with a background, with the patterns that we're studying, and then attack the problem that we're trying to solve, explain how we solve it, explain an old problem that we solved inadvertently, and finally spell out what the solution is. I mean, this background is kind of not, I'm not sure that it doesn't belong with a presentation technically, but in category theory, we either solve a problem or we try to find some general pattern which we're following. So general pattern which we're following here are the decompositions. You know, they say category theory is about composition, sequential composition, parallel composition, but actually more often it's about decomposition. So there are these 3 decompositions which are driving us: Kolmogorov-Arnold, neural networks, and singular value decomposition. You know, in decreasing complexity. So Kolmogorov-Arnold, that is the solution of Hilbert's 13th problem. And Hilbert's 13th problem was to find a function which says that calculus 2 is not a red herring. So to find a continuous function of many variables which cannot be expressed as a sum of single variable functions. And it was open until 55 when Andrei Kolmogorov gave 19-year-old Victor Arnold, he told him, solve Hilbert's 13th problem. And Hilbert proposed so we solve polynomial equations by various formulas. You remember the square, the quadratic equation has that formula, and the solutions depend on coefficients in the equation. So Hilbert says that if we take the solutions of polynomial equation of 7th degree, where A, B, and C are coefficients of 3rd, 2nd degree and constant. So we take a simple polynomial and we express solutions as a continuous function on coefficients A, B, and C. And Hilbert had reasons to believe that these solutions cannot be expressed as sum of single value. This is a continuous function, obviously, that it's not a sum of some number of single variable functions. And Victor Arnold proves that he was able to decompose this 7th degree polynomial solution. And Kolmogorov got surprised, and then he starts looking at that, and he proves a theorem which he didn't believe even after he proved it. So here's that composition. So suppose that someone gives you a continuous function on bounded domain in D variables, function f in D variables. Kolmogorov-Arnold decomposition says that for all such functions, independent on the function, there is the embedding of d-dimensional cube into 2d plus 1-dimensional cube. And it's not a linear embedding. It's a very nonlinear. It's a fractal embedding. So there are d functions psi which embed components, and then there's a linear transformation which embeds these components into the bigger cube. So there's such an embedding of cube independent on the function, such that, and there's similarly a projection of d plus 1-dimensional cube to the interval. And they are such that for any continuous function in d variables, I can find a single variable function such that this function in d variables will be equal, if I embed the domain into 2d plus 1 into the bigger cube, then to every dimension of the bigger cube, I apply the function phi, the activation function, which depends on f. And then I project it back, I get f. So every continuous function can be expressed as a sum, as a mixture of 2d plus 1 single variable functions. And all these elementary functions that you used in calculus 2, I don't know, sinus hyperbolicus, which depends on some function of 5 variables, can be decomposed into functions of a single variable. And it's a crazy theorem, and it's very difficult to prove, and the construction is very fractal. Important thing is that this W and this V do not depend on F. I'm putting in parentheses what depends on F. Only phi depends on F. And this is the version from 1960s, which is even crazier than Kolmogorov's original, because Kolmogorov said, I can find 2d plus 1 single variable functions which will approximate this F. And the approximation goes to the infinity, so it's precise decomposition. In the 60s, Lorentz proved that we can actually push the differences between these functions into W and into psi, and we can do with a single function. Okay, I described this in too much detail. The important thing about neural approximation is that we can turn the tables and we can fix the activation functions and take just anything, literally anything that's not a polynomial will do. So for perceptrons, it was a sine function. In the 80s, it was logistic function. It was sinusoid. Nowadays, it's ReLU in RNNs. In long short-term memory, there's also hyperboloid functions. Anything that makes its way from 0 to 1. And epitome is the Devil's staircase, Cantor's Devil's staircase, which is the function which is a continuous function, and it has derivative almost everywhere, and the derivative is 0, but it makes its way from 0 to 1. But now I can fix these functions, and instead of Kolmogorov's phi's, I can take just anything, but the part which will depend on f will be the linear embedding. So I can now linearly embed the d-dimensional cube into some higher dimensional cube and project back in such a way that I can approximate any continuous function. And there were papers in the 80s saying these neural approximations don't have, the universality was proved in the 80s, don't have anything to do with Kolmogorov. And then people at MIT who didn't read that correspondence from the 90s, they said, oh, we're going to discover the connection with Kolmogorov-Arnold. And they discovered Kolmogorov-Arnold networks, while in 92, it was completely explained that these universal neural approximations are actually closely related, that it's the same approximation process as Kolmogorov-Arnold. And if you want to really, and okay, and I'm drawing the circuit version of these categorical diagrams below, because you're used to drawing your neural networks in this circuit notation. I hope it's clear what it means. You take a d tuple of inputs, and then you hit them with these embedding functions psi, and then you mix them, then you add it all up. So now here it is all embedded in 2D plus one dimensional cube. So we can approximate any continuous function like that. We can approximate any continuous function by perceptron or single layer neural networks, or even more easily and more efficiently with deep neural networks. If you want to understand what's happening, the simplest thing is to look at your linear algebra course from the undergraduate times where we learned singular value decomposition. Someone gives you let me hide this. Someone gives you this time a linear transformation on domain D, and you can find an isometric retraction. So you can project your range into the spectral space, and you can project from there. There's another isometric projection, and in the middle is an isomorphism, non-isometric but invertible, linear, which the way this has been computed traditionally is by calculating eigenvalues, and then the corresponding eigenspaces will diagonalize this matrix. So the simplest case of this decomposition, which we're looking at, is the singular value decomposition, where instead of the activation functions, we have the eigenvalues. So this is the general pattern that we've been looking at. So why will we be looking at this? Well, because the concept mining problem emerged with the web. Before the web, we had databases, and we would specify what concepts are represented by data in the databases. When web came up, everyone was assigning different semantics to data on their websites, and it was difficult to find things. And the tradition of information retrieval was vector semantics. Express words as vectors so that if you express them in the same basis, then the angle between the corresponding vectors will relay the semantic similarity to us. So concepts were linear combinations, mixtures of vectors representing words. So they were mixtures of words. The other way around, if every concept is a linear combination of words, then every word is a linear combination of concepts. So for instance, in singular value decomposition, we are mining for canonical concepts, which are represented by the orthonormal basis. And then we have canonical concept decomposition in terms of words in terms of concepts. However, these concepts are not given to us. We need to search them from the contexts. So basically, we first need to mine concepts as invariant subspaces under the context linear operators. So words will be mixtures of contexts, and concepts we mine as context invariants. That's going to be the practice of what we'll be doing. And now I'm going to slowly try to well, hopefully not so slowly, to steer us to the categorical instance through the intuitions of how we get from context to context invariants, which are the concepts. So here's a simple example, a version of, if maybe people remember from the early 2000s, the Netflix problem. So here is, here's a bunch of people, 5 people, who have watched some Japanese movies. Ozu's, no, this is Mizoguchi's Utamaro and Kurosawa's Kagemusha and Hayashi's Totoro and Ren's Paprika, and they like them more or less. And they have provided feedback in terms of stars. And if you know how much Ed liked Kagemusha and Totoro and Paprika, you want to predict what will he think of Utamaro, which he hasn't watched. but people who have watched some of the movies that he has watched have watched to Tamara. So you want to fill these empty fields, which is the recommender system task. So how can I determine which movies Ed will like among those that he has not seen by starting from those that he has seen? And similarly, what will Bob, Carol, and Dave think of Paprika based on the feedback that they have provided about the other movies that they have watched? So this is already context dependency. The sentence, I don't know, the sentence "I love you" means one thing when I say it, and it means a completely different thing when someone else says it. So I love the movie Kagemusha means one thing when I say it and another thing when someone else says it. So, but we can mine what we all mean from the corpus of feedback that we have all provided about the all movies. So movies that you have not seen, I can predict what you will think about them because I know what you thought of movies that you have seen and what people who have seen the movies that you have seen thought of those movies as well. So how do we mine formally by math the people's preferences out of data sets like this? And you know, this kind of question occurs all across. I mean, I provided example of Netflix problem, but in text analysis, this is the information retrieval. The question goes back to the 70s. The way images are analyzed, elections, and so on. So let's simplify it. Let's dumb it down to yes, no. Let's project away the quantities of feedback, and let's just take into account who has seen which movies. So this is the matrix that we start from. So this is a little bit richer matrix of numbers between 1 and 5, and here we have just a matrix of zeros and ones. So we can present it as a bipartite graph from people who are Alice, Bob, down to Ed, and the movies B0, B1, B2. So this is bipartite graph. Concepts will be complete subgraphs. How do I get that? So here are the complete subgraphs of this bipartite graph. Who has seen all 4 movies? The only person who has seen all 4 movies is Alice. Who has seen the last 3 movies? Well, Alice and Ed. All of that I can derive from the relation. So we want to, so a concept is a pair of sets, a set of users and a set of movies, such that every user has seen every movie, and every movie has been seen by every user. That's what we have. The 4 subgraphs are displayed here, and here's how they work. So in the space D, in the concept space D, there are the 4 complete subgraphs. We connect them with what they are connected, and each concept now then justifies the connection between a user and the movie, because one of the concepts, so the concepts are the concepts of user tastes or of movie styles. And a mathematical proposition that can be proved is that these 2 lattices, they turn out to be lattices, that they are lattices and that they are isomorphic. That the user style, which I can mine from a relation like this, user taste, which I can mine, corresponds uniquely to a movie style, and that although we lack words to uniquely characterize these concepts, there are also always mixtures of words. We can extract the objective user tastes and shared user tastes and shared movie styles, and justify why a particular user has seen a particular movie by the correlation between the user taste and the movie style. So what does this process of extracting concepts look like mathematically? So first I take the set of users and the set of movies and complete them into semi-lattices. So I embed users into the power set of A and embed the movies into the power set of B. The 0-1 matrix, or the relation, which I call here phi, then induces, first of all, well, it induces a Galois connection. If I take a set of let's say viewers, then the set of movies which they have all seen, so I take the set of viewers X, the set of movies which they have all seen is the intersection of the sets of movies related to each of these viewers. The other way around, if I take a set of movies, the set of viewers who have all seen this movie is the intersection of the viewers which have seen all of these movies. So I'm just writing down in naive set theory what I have said, this story about complete subgraphs. So now and this is, you can easily see these two phi lower star and phi upper star they form a Galois connection between these two semi-lattices, power set of A and power set of B. Because they form a Galois connection, the composites of phi lower star, phi upper star, it is a closure operator on power set of B, and phi upper star, phi lower star is a closure operator on power set of A. Note that both are contravariant, which is why they're Galois, I'm calling them Galois connection. They're on both sets and they're contravariant. But, you know, category theorists would probably call them just contravariant adjunction or something like that. But in any case, we have these two closure operators, and the closed subset of viewers is the set of all viewers that have seen. So if I take a set of viewers, map it to the set of all movies that all of them have seen, and map it back to set of all viewers that have seen all of these movies, it will contain the set of viewers that I have started from, and it may be bigger. So it's a closure operator. And it fixes these closed sets, and they are the sides of complete subgraphs of that bipartite graph. And the reason why relation phi relates viewer A and the movie B is that there's a concept in between them such that A's taste is a part of that concept and B's style is a part of that concept. Okay, so we have actually a concept lattice, a lattice of concepts which are here concepts of taste or concepts of style, and it turns out to be join meet completion, a tight completion. I'll define it formally later. But let's try to be a little bit more precise. We have ignored the number of stars there. Suppose that we take into account the number of stars and normalize the feedback to factor out. They always do that, to factor out the fact that some people always give 4 or 5 stars. So 4 stars is negative, 5 stars is positive. Some people always give 1 or 2 stars and they don't provide feedback otherwise. So we may normalize in order to factor out private feedback habits, and we may average things out, and we get some numbers. So we get a lattice where the ratings, each of the viewers' ratings for each of the movies come as numbers, and it's again a sparse matrix because there's many more viewers than movies, and not everyone has seen every movie. So now, given a matrix of ratings like this, with some usually rational numbers, I would like to complete the matrix and to predict what will Bob think of Paprika, or what will Carol, or what will what will add think of, we said, which one was it? So again, we have bipartite graph, but this time it's weighted. So what can we do now? So yeah, we do what we learned in linear algebra. This time the completion under all mixtures would be the vector space with the basis A. So vector space on one hand, we make vector space over viewers. On the other side, we build vector space over the movies as the basis. And now our matrix of numbers between viewers and movies, as usually, it induces a linear operator. The transpose induces the linear operator the other way around. And we, as usually, we call these linear operators, if we have in a product, they will be adjoints, each other's adjoint in the vector space. These extensions, they were extensions to semilattices. These extensions are now how we define the linear operator on an arbitrary vector if we're just given a matrix. So instead of intersections, now we have these mixtures, these sums. And so how do we mine the concept space from this context adjunction now? Well, we look for the invariant subspaces. Invariant subspaces in linear algebra are known as eigenspaces because they are fixed, they are distinguished by calculating eigenvalues. Calculating eigenvalues is a lot of hassle with quasi-diagonalizing matrices because we don't know how to diagonalize them, and God forbid we wouldn't want to go and solve high-degree polynomial equations to calculate eigenvalues. So this is where we begin to learn stuff, because now we can randomly begin from a random subspace, and if we let our linear operator run, the eigenspaces will, in most cases, attract the process to converge, and we will find eigenspaces. So we decompose our linear operator. This is singular value decomposition. We have an arbitrary matrix. At the beginning, we have a retraction, which is an isometry. If it's not a retraction, if it's invertible, then this is what we call unitaries, but this is weaker unitaries. They call them semi-unitaries, I think. In the middle, we have the isometry, which is this, not isometry, isomorphism, which is this diagonal operator. And in the end, we have similar isometric projection. And the concepts are whether we mine concepts as eigenspaces, as the invariant spaces of the Hermitian operators obtained by composing the two linear operators induced by the matrix, or whether they are the eigenspaces mapped to each other. It makes no difference. Well, one way is slightly easier to calculate, but in theory, concepts equivalently occur in both ways. And now we have the same matrix decomposition in terms of bipartite graphs, and the concepts are the justifications, except that now we know which concepts are stronger because they have bigger eigenvalues, and they stretch the space by these scalars. And important thing is that the network traffic paradigm or channel traffic paradigm is different in the formal concept analysis, in the lattice concept analysis. We were just looking for a concept which would justify relationship. Here, since we do linear algebra, for each concept, we calculate the path. So 3 times half times 55 plus 0.3 times 1 times 6 will give us the justification, the rating of viewer A for the B1. So in a sense, while the network traffic formal concept analysis was from the standpoint of a driver or a particle is just looking for a certain path to cross from A to B. When we do it by linear algebra, it's the wave network traffic. It's from the standpoint of, let's say, urban designer. If there are two freeways from A to B, we are looking at all traffic through both freeways, and we add them up, and they interfere. When there's more traffic on one of them, when there's a traffic jam on one side, then we go on the other side. So there's interference in linear algebra, and that causes problem. That's what brought us with our little category theory suitcase in the business here. Because, you know, wave mechanics, it's all about interference. When we go from quantitative waves in neural networks to semantical waves, we calculate amplitudes of these interfering waves. While on the other hand, since we're doing linear algebra, when we're multiplying these matrices, if matrices happen to be stochastic, if they happen to be matrices of probabilities, then the very fact that we're multiplying these matrices injects the tacit assumption that the correlations that we observe in the two matrices are stochastically independent. So, you know, when the fact that the probability, conditional probability, if I see I, my chance that I will see J is some sum of products of probabilities through gamma, means that I and J must be independent on all of these, statistically independent on all of these gammas. That is what the fact that composite probability is the product of component probabilities. But if they are statistically independent, then every correlation is causation. And in these implementations based on linear algebra, which is all of them, I mean, everyone is using this latent versions of latent semantic analysis, both Amazon and Meta and everyone. As soon as you do linear algebra, the algorithms say that all correlations need to be amplified, and we have lost track of statistical dependencies, even of previously mined concepts. So what can be done? If we have these matrices of numbers, then the interferences will be masked as soon as we proceed with linear algebra. That's kind of funny. I mean, what we were thinking is that this is the end of the world, because at the time when we started working on this, it was the time when there were all these terrible echo chambers and Pizzagate, and people were getting these crazy ideas, and everyone was thinking these echo chambers are because Zach is a bad guy and he wants to attract people, and he amplifies all correlations in order to glue the users, which would solve the problem by simply removing the malice from the business models. And then it turned out that the malice of business models was actually not in the business models, but it was in the linear algebra that we were using. And that was pretty astounding, because, you know, this statistical independency assumption wasn't never explicitly made. It was the tacit assumption following from the fact that we were multiplying matrices. So what can be done? Well, what could be done? No one was smart about it. People were already doing it. Instead of working with matrices of correlations counted as in information retrieval times, as in Gerald Salton's times in the 70s, they were making databases of transactions. So I did not count how many stars Alice gave to a certain movie, or how many stars Alice gave to a certain item on Amazon, but I counted how many transactions of a certain type did Alice have, and it was stored in the database. And database items were the entries, database fields were the entries of matrices. So matrices were matrices of sets of data rather than of data counts. So instead of having or just counting that Alice, who is it? Carol and Totoro, that Carol saw my neighbor Totoro 3 times, I recorded the events where she had seen them, so that when I mine the concepts, I can distinguish each event occurring from different concepts. So I'm just justifying how nature brought us from matrices of numbers to matrices of sets. And then in order to record previously mined concepts, we can say that the dimensions of matrices, they are not just sets, they're not just vanilla bases, but that they have structures, that movies are related among each other. Some are more sharper comedies, some are more love movies. Users are related with each other. Someone loves all the movies which someone else loves. And the actions of these previous conceptual relations on the currently mining data actually help with mining. So that's how we came from ordinary linear algebra to categorical matrices known as profunctors or distributors or whatever. They are, in any case, they capture the concept interferences, which was the problem that we started from. And the concept interactions once we figure out how to mine them. So that's the task. We want to repeat that same workflow, decomposition workflow, which we saw on lattices in formal concept analysis, and which we saw on linear operators, on matrices of numbers in latent semantic analysis. Can we do that same thing on matrices of sets? That's the question. So here's what that would look like. I started from let's say posets A and B, and I completed them to 3 semilattices, which induced Galois connection. I had closure operators, and the concepts were the fixed points of these closure operators, the closed sets of these closure operators. Up from posets to categories, I can complete one category not to semilattice, but to its co-limit completion, and to the other category to its limit completion. My profunctor will then induce 2 Kahn extensions, the left and the right Kahn extension between these completions, and that will give me a monad and a comonad where all the closure operators were, except that in the posetal case, the monad, the closure operator, and the comonad, the other closure operator on the dual poset, the fixed points, the fixed point lattices were isomorphic, and the fixed point lattices, quote unquote, fixed point lattices of a monad and a comonad would be the categories of algebras and coalgebras, and they don't tend to be isomorphic all that easily. They don't tend to be even equivalent. So what do I do? So we have this adjunction, and how can we find the concepts which this adjunction is fixing? So the concepts will again be invariants, and algebras and coalgebras do some of the invariant stuff. They are fixed in a certain way, but they are fixed as idempotents. up to idempotent. So there's some lifting to be done. So here's the task, and now, and we want to decompose this profunctor into two profunctors going into, and how we compose profunctors is via coins, going through this concept category, which we need to define. So I don't know how much time. Oh my God, I have spent 40 minutes on defining what my task is. So here is the lattice case. I have a matrix of zeros and ones, or a binary relation. I have a mapping from users to sets of movies, or from movies to sets of users. I extend them to join preserving to semi-lattice morphisms, and I get this Galois connection. We've seen this Galois connection. I can do that same thing with so you give me a profunctor. I have a representation of the first category in the, so here I don't want to call it's terrible to me to call the elements, the covariant functors from B co-pre-sheaves. It's like you have twins and one child is called Elizabeth and the other child is called co-Elizabeth or something. But people hate when I call them post-sheaves. So these post-sheaves are like upper sets and pre-sheaves are like lower sets. So let's call them left. Okay, let's call them discrete fibrations and discrete top fibrations, but the category of discrete top fibrations is opposite. So we have this representation and we have two Kahn extensions. We have this is the left Kahn extension and this is the right Kahn extension, and they're adjoint. And so that's how we formalized it. In order to state this simply, and people were already doing this before when I got there, they didn't even know what a category was, although they had profunctors implemented. So to not have to define the two categories of monads to them, or two category of adjunctions, especially since both these two categories, the only two cells which are allowed are isomorphisms, because if we need both free algebras and all algebras, both Kleisli and Eilenberg-Moore constructions, to have their distributivities, we need invertible two cells. So we're assuming that all categories inside are skeletal and that they're absolutely complete. That can obviously be achieved for every category. And what we get is that the only place where these two cells play the role is once we go through training. There is something called Minsky-Papert theorem, which says these things are indistinguishable by this family of neural networks. In their case, it was the perceptrons, and there we do have these groupoids of two cells, but we're not interested in that now. And if we're not interested in that, we can absorb the two cells into one cell. We can just take two cells and take the two cells to be composable, and we have one categories of ordinary categories of adjunctions, monads, comonads, everything being up to isomorphism will here mean that wherever we have pseudo things, wherever we have equivalence, we can find an isomorphism of categories. So when you have equivalence of two skeletal categories, the equivalence will certainly be coming in the same, will be identity on the object, because there's only one copy of an isomorphic object, and then you can transpose your equivalence along the isomorphisms which are in groups of automorphisms on these objects, and you will have an isomorphism of categories. So everything that I'm saying that I will be spelling out is ignoring, well, it's not ignoring. It has legitimately projected away the two categorical aspects until we need to deal with them within distinguishability. And here's the main theorem which brings us in the business. You give me an arbitrary adjunction. The only requirement is that we will have performed absolute completion. So these categories that we're looking at are all idempotent split, and they're skeletal. So you give me an arbitrary adjunction between two such categories, and then the adjunction will induce a monad on one of the categories and a comonad on the other of the categories. People don't like this notation and tell me that I'm inventing it. I'm inventing it insofar as I read SGA 1 from 1958. The notation is mostly due to Grothendieck, and in the meantime, people got into worse notation, but I can't recall writing. So this is my Eilenberg-Moore category. It didn't exist, of course, in Grothendieck's time, but it did exist when what's his name called them standard constructions. In any case, so here's the monad induced by this adjunction. Here is the Eilenberg-Moore category for the comonad. Here's the Eilenberg-Moore category for the monad. So given an adjunction, I have monad and a comonad, and I also have Eilenberg-Moore category for the monad and Eilenberg-Moore category for the comonad. The claim is that then there is an adjunction between algebras and coalgebras induced by the original adjunction, such that, well, there is an adjunction which happens to be monadic and comonadic. What that means is that if I repeat the construction, so I have an adjunction here, and that adjunction induces a monad on one side, monad on coalgebras, and a comonad on algebras. The category of coalgebras, Eilenberg-Moore category of coalgebras over the category of algebras is equivalent with the original category of coalgebras. And algebras over coalgebras are the original algebras. That's the nucleus theorem. So it's kind of pleasant. It's the question which was asked by Mike Barr in 1968, and he got confused because Miles Tierney was claiming that the infinite towers of resolutions which he and Applegate were building were infinite, but that is not the same as this iteration. So how do we form I'm kind of hoping that people will interrupt me if I'm rushing now to make at least the statements. But if anyone has any questions, just yell over me and I'll stop. So how do we, the adjunction between algebras and coalgebras is the simplest possible. From algebras, you have forgetful functor into A, and for A, you have the comparison functor into coalgebras. The comparison functor takes an object of A into the image of the unit on that object. That is the coalgebra. So I will, and similarly with coalgebras, I have the forgetful functor, and I'm going to go along the forgetful functor and along the comparison functor, and I'm going to go from coalgebras to algebras. So it looks pretty crazy. It looks like I take algebra, forget its structure, only remember the carrier, take the unit and map it into coalgebras, and that is my coalgebra. And similarly, I take the coalgebra, forget the coalgebra structure, and forget it and form a close approximation to free algebra. The structures are not forgotten because the claim is that I have an adjunction here, and the structures are remembered as the unit and the co-unit of the adjunction. Why is this an adjunction? So that is the confusion which I was walking around with for a year, and a student from Japan, Toshiki Kataoka, helped me, and we proved that the adjunction actually goes the opposite way. It goes the wrong way. You see that the right adjoint becomes the left adjoint. The right adjoint between A and B becomes the left adjoint between algebras and coalgebras. And left adjoint becomes the right adjoint. How does this adjunction correspondence, this backwards lifting of Kahn extensions work is, so if someone gives you underlined F, you will get its transpose by taking the image of the underline F, recomposing it with coalgebra, and you will get the mate, the adjoint mate, and the other way around. Hence this bijection, and it turns out to be natural. It's much harder to prove that the nucleus, that these two functors, F sharp and F lower sharp, F upper sharp and F lower sharp, are monadic and comonadic, and that is in our nucleus paper. You can read it about that. But what happens is that we have two resolutions. We start from an adjunction. We have monad resolution, and we have comonad resolution. And the nucleus is the intersection between the two. Because we are in this world where we have equivalences become isomorphisms, this is on the nose idempotent monad on the category of adjunctions. So idempotent monad takes an arbitrary adjunction and always gives you an adjunction where the right adjoint is monadic and left adjoint is comonad, which means that each of them determines each other. So they're not isomorphic, but one is enough. And the workflow is the concept analysis and data mining workflow is that we begin from a data matrix, we complete the two sides, maybe with previously mined concept into an adjunction. We work out two resolutions, resolution of a monad and resolution of a comonad, and we spell out the nucleus. And we have the adjunction of canonical concepts, which determine each other. But they determine each other in a slightly mind-boggling way. So while for posets we would have an isomorphism between concepts on the user side and concepts on the movie side, here we have algebras which reconstruct the coalgebras as coalgebras over algebras, and we have coalgebras which reconstruct algebras as algebras over coalgebras. So nuclear adjunction is an adjunction where this operation of constructing the two resolutions doesn't take us anywhere. We remain with the same adjunction, which here it's written equivalent, but it's actually isomorphic. We don't get anything new. We have two concept spaces which completely determine and live in each other in a certain way. So the original, then the corollary will be that the original resolution can be simplified. So with the original resolution, here we had coalgebras, and here we have algebras, and the comparison functors take A into some coalgebra and B into some algebra. But we actually here are equivalent and much simpler, for implementation at least, versions of Eilenberg-Moore constructions. Here we have the category of where objects are projective algebras. They are the coalgebras. And here we have a category where the objects are, again, idempotents, the injective coalgebras, and they are the category of algebras. And they lift the original adjunction on the nose, on the objects, and on the nose on the idempotent. So here's what the upshot of the nucleus theorem looks like. Coalgebras are coalgebras of algebras. So if I have the category of algebras, I can represent them as coalgebras over algebras, and I have this simplified version of Eilenberg-Moore and simplified version of Eilenberg-Moore in the presence of adjunction for coalgebras as well. What can we do with that? And okay, so here are these simplified categories. So the category of coalgebras will be equivalent to the category where the objects are pairs, an object of A and an idempotent over image of that object in B. If you stare at this idempotent for the moment, you will see, you will realize that since this F upper star, that's a left adjoint, then by adjunction, the transpose is just a Kleisli morphism in A. So you can think of these objects as an object in A and an idempotent Kleisli morphism on that object. So here we say that it's idempotent. And here we say that so here is that idempotent. And here we say that it splits on what in Eilenberg-Moore would reconstruct for us the algebraic structure on coalgebras. Which coalgebra is this? This is the coalgebra which splits, into which this idempotent splits. And then you would say that category of these objects, since it is an object in A and an idempotent in the Kleisli. Well, if we split idempotents in the Kleisli category, we get, in Kleisli category, we have all three algebras. Idempotents are retracts of three algebras. So if we split idempotents in Kleisli category, we will get the category of projective algebras. So these objects would be the category of projective algebras, would correspond to coalgebras. Well, category of coalgebras is not the same thing as category of projective algebras, but we're not claiming that it is. We're claiming that objects are given in the same form, but morphisms are different. Morphisms between idempotents would have the same requirement. So here we have an idempotent, here we have another idempotent. Morphism between idempotents would require that this square commutes, and moreover, this F star F also goes through here along the diagonal, and also a diagonal would need to commute. So the category of projective algebras would have a smaller, more constrained family of morphisms. If we relax the idempotent morphism from the diagonal, then projective algebras are nothing but coalgebras. And similarly, injective coalgebras are nothing but algebras. So this was spelled out in detail in a paper because we used it for some security application in LIX 2017. So in any case, we get, so what we got so far is that we can always get a nuclear adjunction, and we get a better, simpler representation of Eilenberg-Moore construction. Someone had to leave. So I'm sorry if I'm overrunning. Yeah, I have 1 more minute. So the traditional, the old problem that this solves for us is the problem that we started from, the tight completions. So here is, I'm gonna just say tell you what we're doing. Here's how, here's the best known tight completion. You start from a poset of rational numbers, you embed it into its upper semilattice joint completion of lower sets in rational numbers. You embed it into lower semilattice of upper sets in rational numbers, that is its meet completion. You have you're mapping lower sets into the corresponding upper set of upper bounds, each upper set into the corresponding lower set of lower bounds, and you have that Galois connection. You have two closure operators. Each of these closure operators has closed sets, which are the lower sets, which are the lower sets of all of their upper bounds. And pairs of such closed lower set and closed upper sets are what we know as Dedekind's cuts, which was Dedekind's construction of real numbers. The whole thing lifts as McNeil's tight completion on posets. What does it do? So McNeil's tight completion, it's the completion under joints and meets. It has all joints and all meets. It is generated by joints and meets. And the most demanding part is that the embedding of the original poset into the completion is tight, which means that it preserves any joins and meets which might have existed in the original poset. This says that if you begin from a complete lattice, from a poset which has all joints and all meets, that you should get back that poset because all joints and all meets should be preserved. So now we lift that. The old problem was stated by Lambeck in 1964. We want to lift that to categories. We want a category completion of a tight completion of a category C would have all colimits and all limits. It would be generated by limits and colimits, and it would preserve any limits and colimits that might have existed. That's what Lambeck asked in volume number 24 of Springer Lecture Notes in Mathematics. It is an open problem whether there exists a super-naive category with super-naive dense embedding. Lambeck proposed that we call limits infima and infima in categories and co-limits suprema, and it is the testimony to MacLean's bad taste that we call them limits and co-limits. It would be nicer if we call them suprema and infima, but it's not the worst loss that we've had. And then John Isbell pursued that question, and after I think 3-4 years, he wrote a paper about small categories, and somewhere he defines Lambeck extension, this tight completion, and proves that Z4, that the group with 4 elements, doesn't allow tight completion, and the problem was shut. But actually, there is but from implementation, we knew that there is a family of limits and colimits which do approximate each other. So if we repeat, so now I'm going to hurry to finish within a reasonable, maybe another couple of minutes. Zainab is not yelling at me that I should. I was expecting that.
Yes,
Zainab
I want to leave a bit of time for questions. So if you could finish, yes.
Yeah,
thank you.
Okay, so here's what we're doing. This is what we'd like to do. With poset, we have an isomorphism here. With how we get out of the fact that we don't have isomorphism is that we notice that if we take these adjunctions in Lovier's in comma format, that we will get 2 comma categories, well, 4 comma categories, pairwise isomorphic, and that these 2 isomorphic posets, the isomorphic concept lattices, will have a 3rd isomorphic concept. Well, you know that with cuts, that having just lower cuts is enough, having just upper cuts is enough, but to calculate more easily, we take cuts to consist of a lower cut, such that upper cut is the set of its upper bounds, and the upper cut such that lower cut is set of its upper bounds. So they're next to each other, and they determine a real number. So on the right hand side, we have now 3rd isomorphic category, which is, or 3rd and 4th isomorphic lattice, which are these 2 comma lattices. What happens is that in the left adjoint, we have a lower set which is contained in the set of lower sets of the upper. We have a pair, lower set, upper set, where lower set is contained among the lower sets of the upper one, and the upper set is contained among the upper sets of the lower one. So we have a gap, if you like. The join of the lower set is lower than the meet of the upper set. On the right-hand side, we have the opposite, that the upper set contains the upper sets of the lower set, which means that the meet of the upper set is below the join of the lower set. So they are an interval. Here I show it. So join of the lower set is below the meet of the upper set, and the other comma gives us the opposite inclusion. So for posets, we get the cuts. Now I'm in the business. Now I know what to do. With categories, I can do this. On the left-hand side, with the left comma, I have gaps again. And on the right-hand side, I have intervals implemented by categories. I don't have time to hold that, but together, they are determining these cuts, which are determined, and I'm not going to go through the proofs. These cuts are actually splitting the structures of algebra and of coalgebra. So we can, if we know the cut, we can omit the structure of algebra and coalgebra and simplify things away. And in the end, we have this category of cuts, which would be the tight completion of the category C. So cuts in posets they form the concept lattice. The concept category would be formed in exactly the same way from these two commas of by crashing gaps and intervals, and they would be just a single point gaps and single point intervals, and the tight completion in that category gives us actually the limits and co-limits which are approximating each other are what Peter Johnstone had called not filtered, but they are the completions. I forget the name Peter Johnstone gave them. They are the completions of category of algebras. So there are these two families of limits and co-limits which when you complete under one family, you have completed under the other one. They behave like meets and joins with respect to each other. And then we proceed back to profunctors, and we can do the same thing. We have cuts with respect to profunctors. We define the category of cuts, and we have the category of concepts. And that turned out to be actually easier to implement than a vanilla adjunction. Sorry that I overran, but I'm telling you about stuff that I had to think about for 10 years before it occurred to me, before the couple of tricks that were missing occurred to me, and it was too tempting to me to not tell you everything, so I tried to tell you everything, and I hope it wasn't too incomprehensible. Sorry to overrun.
Thank you very much. Are there any questions?
Of course, I intimidated everyone by running too fast, and no one will ask any questions. I'm sorry about that, but everything that
I had a couple, but if I don't see anyone, I'll ask my questions. So the first one, I just want to clarify the terminology. What I'm used to is nucleus of profunctors is the center of the first adjunction that you have.
What is
so in your notation, it's phi lower star and phi upper star. So, but you're using nucleus for a different.
That's again. Let me see. I have done this, and I'm trying to reappear myself so that we don't speak. I have removed my my own picture, and now I don't see myself. Do you mind that I'm speaking without?
Yes, it's okay.
Okay. The schema, the place of the nucleus in the first diagrams which I have shown,
Right.
the term nucleus goes to 1954 in Grothendieck's thesis, where for the operators between topological vector spaces, the kernel which he was calculating, he called it nucleus because I think Borshuk had called nucleus the corresponding construction on Banach spaces. And then people, because it's so difficult to calculate the nucleus for categories, then they started, people tend to do that. If I can't calculate what is normally called nucleus, then I'm going to call what I can calculate, I'm going to call it nucleus and declare victory. So I don't know what the center of an adjunction is, but I know that what people call tight completions is very far from what has been called tight completions in both lattice theory and in early category theory. But it was what people were able to do. It's these comma categories. So hence the terminology.
Okay, so my second question is, if your profunctor itself is a monad, so a permonad, a monad internal to prof, what happens to this adjunction?
Everything,
Do you have extra properties?
No, everything that I have said could be stated entirely in terms of profunctors by skipping the completions. The role of completions is that it allows me to reduce the profunctor to an adjunction. If I complete my two categories of the profunctor, my profunctor becomes representable as an adjunction. And that was easier to explain to people. But then, on the other hand, if I went to the profunctors, I wouldn't have any, in order to make things implementable, I have even eliminated the equivalences in order to, in favor of isomorphisms. If I stayed with profunctors, I wouldn't even have any equivalences because the statements which I have made would be up to Morita equivalence, up to weak equivalences. And it would be, it's like when people do, well, it's a little bit like what Grothendieck was doing in his thesis. To be able to state all the theorems in a comprehensible way, Banach and Borshuk assumed that our topological vector spaces, not only they have either inner product, separated inner product, or are complete with respect to the norm, but that they are complete, and everything inside is representable. And then if I want, without that representability, I have to, everything becomes complicated to say. So everything that I said here could be stated entirely without representability in terms of profunctors, but it would be really mouthful to say.
Thank you very much. Any other questions? Okay, if not, well, thank you very much again. If you don't mind, could you please send us your slides so that we can post them and people can look again at to be able to look at your slides again.
Certainly. I apologize that I tried to say too much. Person my age, after having given millions of talks, should know better. But you provided me an opportunity to tell my story, so I didn't resist the temptation.
Thank you very much for coming again.
Thanks much.